For example, if I flip a coin, what's the probability of getting a head? 50-50 would be odds, not probabilities. That's a different idea. It would just be 50%. Okay, so odds have to do with like when you're gambling and there's payout. That's when we use 50-50. And that's only true if we believe the coin is not weighted, that there's just as likely to come up heads as come up tails. But do we really know that for any coin? The answer is no, we really don't. With theoretical probability, the assumption is that you believe that you have complete knowledge of the situation. And then you can make those predictions, like the probability of a head is 1/2 or 50%. 2, we have empirical or experimental probability. And that's a situation where you really don't know. For example, what's the probability that I can throw this box of markers into the trash over there? 45%? Okay, I was thinking it was 50% because either it's in or it's out, 2 outcomes. But the problem is we do not know, ooh, that was bad, I missed. We do not know if those 2 outcomes are equally likely. We don't have the complete knowledge of the situation. You don't know my skill. And so the only way to figure that probability out is to do a bunch of experiments and count. Okay, so with experimental, we have to watch and count. Okay. Then there's other kinds of probabilities. Like, did anyone check a weather app or website to see if it was going to rain today? Is it going to rain today? No? Okay. So sometimes we look at those apps and they say, hey, there's a 60% chance of precipitation. What does that mean? They're giving us a probability. Does that mean 60% of the day it will rain? Does that mean in 60% of Pendleton it will rain? The heck does that mean? Did they actually watch 100 days and say, hey, 60 of these days it rained? Right? So there's these other kinds of probabilities that are just these expert guesses. Because they're not experiments, they're not theoretical, we don't have complete knowledge, okay? And so the probability that it's going to rain is one of those. It's not theoretical, it's not experimental, it's some interesting blend. Similarly, I was looking at polls coming up to the presidential election yesterday. And for a while, they were predicting Hillary Clinton had an 85% chance of winning, and Donald Trump had a 15% chance of winning. That was yesterday morning. Didn't quite turn out that way, did it? Donald Trump really took advantage of that 15% chance. It's now 100% chance, okay? But that was neither theoretical nor experimental. It was a blend of them, okay? So there are different kinds of probability. Sometimes the guesses involve theory, involve experiment, okay? But those are the kinds of things that we're working with. So let's take a look at a theoretical one first, I think. Roll 2 dice. And then we want to figure out what's the probability, and a lot of times I'll abbreviate probability with a P in a parentheses, that the first one is maybe a 3 and the second one is even. So in order to keep track of what both dice are doing, I need to carefully map it out some way. And we have 2 ways to map out situations like this. One way is to draw a tree of all the possibilities. So let's see, how many possibilities are there for the first dice, or die, excuse me? There's 6, right? And how many possibilities are there for the second die? There's 6. So altogether, my tree is going to have 6 times 6, or 36 end branches. Okay, so it's going to be a fairly large tree, even though this is a relatively simple situation. If there's only 2 things going on, another alternative, so for only 2 things, 2 dice, for example, you could make a table. And so I'm going to make a table instead of a tree right now. Okay. So the table for this is going to show the first dice on one side and the second on the other side of the table. And then I have to list all the possibilities for the first dice and the second dice. So the first dice could be a 1, a 2, a 3, a 4, a 5, or a 6. And that's going to generate the rows of my table. The second die could also be a 1, a 2, a 3, a 4, a 5, or a 6. And that's going to generate columns in my table. And then what I want to do is kind of use that table to isolate the information I was given. So let's see, what was I given? First thing, getting a 3, okay? We can get a 3, let me get my highlighter. Control T, there you are, highlighter. And you are, come on, highlighter. I need yellow, please, there we go. So first dice getting a 3 could be anything in that row right there. So there's 6 possible ways I can get a 3. Second dice can do anything it wants. But I wanted the second die to do something very specific. What did I want the second one to do? I wanted it to be an even number. All right. Well, 2 is an even number, 4 is an even number, and 6 is an even number. So how many locations do we have where the first die got a 3 and the second one got an even number? Now, there's 3 possible places that can happen. So that happened here, that happened here, and that happened here. So when we're talking about experimental or theoretical, it doesn't matter. The numerator of the probability is always favorable outcomes. There are 3 favorable outcomes for this situation. And the denominator is always all possible outcomes. How many possible things can happen with 2 dice? We already figured, yeah, 36. So 3 out of 36 is 1 answer. With probability, I usually don't worry about reducing it. I do 2 things. I state the fraction, whatever it is, and then I state it as a decimal or a percent. So find me that number as a decimal or a percent. What would it be? What is that? 8.3%. Okay. So and usually with percentages, we give to the answer to the nearest 1/10 of a percent. So the answer is probably like something 0.08333333 going on for a while. And those 3's keep repeating there. To change to a percent, recall, oops, wrong color. There we go. We move the decimal point twice, so it's around 8%. Giving an extra 1/10 there gives us 8.3%. And so you just want to pay attention to the homework questions. Do they say state a fraction or a decimal? If they state a fraction or a decimal, safe bet, enter the fraction. If it says enter percent, pay attention to how many decimal places they want in their percent. Or if it says state a decimal, pay attention to how many decimals they want in that decimal. Okay, and try not to mix them up. That's often where things go wrong. Stating the answer. All right, let's try another one like this. Let's stick with 2 dice. And I want to find the probability that after I roll them, the sum of the dice is, let's go with, how about 6? So now we've got a little more work to do because we got to figure out the sums for all of the dice. But we can do that. So I'm going to redraw my table. All right, so first dice could be a 1, 2, 3, 4, 5, or 6. Second dice could be a 1, 2, 3, 4, 5, or 6. So what I'd like you to do right now is start filling out the sums inside this table so we can figure out what the answer is. So for example, if I get 2 1s, my sum is 2. A 1 then a 2, my sum is 3. A 1 then a 3, the sum is 4. Adri, are you all right? You don't need to participate? You don't need to participate? You already did the homework. Do you have any questions? No. Okay. All right. I'll get to some more interesting problems in a few minutes. All right. Everyone else that didn't do the homework, play along. You should see a lovely pattern develop. Something like that. So the easy thing about probability problems is they involve counting, but unfortunately sometimes counting is very hard because you got to find an organized way to do it. So here I see 6s along this diagonal here, and I have 1, 2, 3, 4, 5 6s. And so I think then the probability should be 5 out of what? 36? Yeah. That's a fine answer, 5 out of 36. If we were asked though to give it as a 0.1%, then we'd have to whip out a calculator. Google says 5 out of 36 is 0.138888888. So if it said, give me an answer to the nearest 0.1%, what would my answer be?
$13.9.
13.9%, yeah, good. So we could say, and that's an approximation, so a little curly equals there. So it's about 13.9, almost 14% of the time we should expect to get a 6 if we roll 2 dice. There's a bunch of different ways that can happen. All right, so I'm going to back off and give you a slightly easier question to go over an idea. So let's say you flip 2 coins. If you flip 2 coins, you could either get 0 heads, 1 head, oops, or you could get 2 heads. So I would like to know, what is the probability of getting 1 head when I flip 2 coins? So write something down before you answer that. There's 2 reasonable answers here. One of them is wrong. Anybody want to take a stab at it? Oh, 1 out of 2. That's a good answer. Anybody want to take another stab at it? I was thinking 2 out of 4. Aren't those the same? Yeah. I was also thinking, well, couldn't it be 1 out of 3? There's 3 possible ways you can get heads. 0 heads, 2 heads, 0 heads, 1 head, or 2 heads. There's 3 outcomes as far as counting heads go. Okay. However, are each of those outcomes equally likely? That's always the question that we have to raise. Well, when you have multiple things happening at once, it's always a good idea to draw a tree or make a table. Let's draw a tree this time. So my tree would be the first coin happens and I either get a head or a tail, right? That you can think about splitting reality into 2 different futures. One future, I got a head. Well, if we follow that future and we flip again, well, we're either going to get a head or a tail, right? But we could have been in the other future, right? Like yesterday, there was probably another future, some alternate universe where Hillary Clinton won instead. We unfortunately are not in that universe. Could be a head or a tail there. How many outcomes does my tree show me?
4.
There's 4 outcomes, right? Because we have 2 things happening, each with 2 outcomes. 2 times 2 is 4. There should be 4 possible outcomes here. So my denominator for this problem should be 4. Okay. So that makes this guy right here questionable because it has a denominator of 3. And if we look at this tree, the first branch at the top says, hey, 2 heads happen there. If I follow this second option here, only 1 head happened there. Head then a tail, but it could have been a tail then a head, and that is a totally different reality. Or I could have had 0 heads if I follow that last branch. So as far as counting how often each of these happens, there was 1 way to get no heads down here at the bottom, but there were 2 different ways to get 1 head. And there was only 1 way to get that head. So the correct answer is either 2/4, or you could reduce it to 1/2 if that makes you happy. Okay. Other possible answers state the decimal 0.5 or rewrite the decimal as a percent, 50%. But the 1/3 is definitely wrong because there's 2 different ways we can get a single head. We could get that head first and then a tail, or get a tail and get that head second. Okay. So the key about probability is carefully counting all the options and keeping track of them. Right? All right. Other things to consider with respect to a tree. And let's continue with this one. Sometimes when I draw a tree, I write the probabilities as I go. For example, what's the probability of getting that first head?
1/2.
Yeah, it's 1/2, right? So I could write the 1/2 on that branch. What's the probability of getting a tail? Well, that's 1/2 too. Okay. Does the probability change at all when I flip the second head? Second coin, sorry. Or is it still 1/2?
No, it would change to 1/4.
No, what's the probability of just, so right here, what's the probability of getting a head? I flip a coin. What's the chance I get a head? It's 1 out of 2. Yeah, it does not change. When events follow each other like this and don't change, that's called independent events. Hopefully you read about independence when you were doing the book stuff. Independent. Independent means one event does not affect another. I'll give a formal definition of it in a minute. Okay. When I flip that coin a second time, or I flip that second coin, it doesn't matter what happened before. The coin does not care. Okay. Are 2 events always independent? The answer is no. For example, me trying to throw the markers in the basket. The first time I threw it, I missed. I'm now nervous. I go for the second shot. I'm probably less likely to make it because I'm nervous. Or maybe I get it in. I'm relaxed. I feel good. I'm hot. I can get it in again. Right? That might up the probability of getting it in again. Okay, so we can't assume events are independent. We have to really think about it in every situation. Okay. So independence means the probability doesn't change from one trial to another. So the probability of getting a tail the second time, well, that's still 1/2. Probably getting a head the second time, that's still 1/2, and that's still 1/2. Now there are 4 possible results at the end of this tree. Top branch says I get a head. Next branch says I got a head followed by a tail. Next branch says I got a tail followed by a head. And then I got a tail followed by a tail. So those are my 4 different outcomes. Getting a head or a tail, they're equally likely, aren't they? Yeah, so if you have branches and everything's equally likely along the way, that means each of your end results are equally likely. So what's the probability of getting a head then a tail? Well, there's one way that can happen out of 4 possible outcomes. So that probability is 1/4. Another way to think about it, though, I'm trying to find the probability I get ahead on the first flip and I get ahead on the second flip. And it turns out when you have an and here in the middle, if the events are independent, this is important, they got to be independent, then the answer is the probability of the first flip, oops, times the probability of the second flip. I can just follow through the tree and multiply, and that's going to give me the final probability. So I have a couple of ways to think about that. So if 2 things are connected by an and, if those events are independent, we can just multiply each result and that'll give us the final answer. But we have to have independence for that to happen. Independence means one event does not affect a future event, or looking back, some event is not affected by anything in the past. That's independence. So the kind of shortcut definition for independence is that the probability of A and B happening, if the events are independent, has to be the same as the probability of A times the probability of B. So this goes both ways. If that's true, they're independent. If they're independent, this equation has to be true. So it turns out probability is all about counting, but there are some guidelines to how that counting has to work and how things relate together. And we summarize those in a bunch of formulas. All right, I'm going to bring up a problem from your homework. Let's take a look at number 4. Okay. Screenshot this sucker. Oops, wrong button. All right, so we are giving a test to a group of students, and the grades and gender are summarized in the table here. So if one student is chosen at random, we want to find the probability that the student did not get a B. So before we do that, let's find the probability that a student did get a B. Well, if we look here in this column, those are the B's. A total of 12 students got a B. So for getting a B, there are 12 favorable possibilities. And then there are a total of 44 students that took the test. So the students that got the B must be 12 out of 44. Okay? And we could turn that into a decimal and clean it up, but let's not worry about that yet. What we want to know is what is the probability of not getting a B? And it turns out there's 2 ways we can do that. One way would be to look at this and say, okay, let's see, how could you not get a B? Well, according to this table, students either got an A, a B, or a C. And I can look at this and say, okay, 9 of them got A's, that's not a B. And according to this, 23 of them got a C, that's not a B. So 9 plus 23 out of 44 is another possible answer. Let's see, 9 plus 23 is what? 32? All right. So I think the probability of not getting a B is 32 out of 44. Another way to look at it, would you agree either you got a B on the test or you didn't? What happens if we take the students that got a B and added those to the students that didn't get a B, what do we get? We get all the students, right? So couldn't I take another approach on this? The bottom line is the probability that something happens combined with the probability that doesn't happen, those always have to add up to 100%. So my belief then is that if I start at 100%, which is 1 as a number, I can just subtract the other probability. So the opposite of not getting a B is what? Getting a B. So I think the answer is also the same as 1, 100%, minus the probability of the opposite, which was 12 out of 44. So let's just double check this. So on your calculator, what's 32 out of 44? And then try that other calculation and see what we get. Madeline, you get a calculator? Play along, it's fun. So we've got, what was it again? It was 22 out of 44? No, it was 32, thank you. 32 out of 44. So that's 72, almost 73%. Alternatively, I believe I can get the same answer by going 1 minus the other probability, and the other probability was 12 out of 144. And that gives me the same number, okay? So we get a couple of different ways we can work with stuff. And sometimes it's easy, it can make the problem easier to switch, okay? So the question is back here, if I already know this probability, is it easier to do a 1 minus it to get an answer? Or to figure out all the other possibilities and add them up and then divide? A lot of times, this is going to be the easier route. Okay? Especially if we had to do like A, B, C, D, F, because then there would be a lot more ways one could not get a B, and we'd have to find all of them. Okay? So this is a rule that's summarized. The probability of not event, so not A, is always going to be 1 minus the probability of A. And not A and A can be switched. So I could easily rewrite that. If I could get my colors back. Someday I got to figure out why they keep disappearing. So alternately, this could be rewritten as the probability of A is always 1 minus the probability of not A. So that's another useful formula. All right, let's see what else was exciting on the homework. Number 6 was interesting. Oops, that's probably bigger than I wanted. I wonder if I can just copy this. See what happens. I think I can. Ooh, then I can adjust it. Excellent. Can I make the font bigger though? Oh, maybe. Okay. So here's our situation. Enrique buys a bag of cookies, and there are 8 chocolate chip, 4 peanut butter, 4 sugar, and 8 oatmeal. So he's about to have a sugar party, and we're then asked, what's the probability that Enrique reaches into the bag and randomly selects a chocolate chip cookie from the bag, he eats it, then he reaches back into the bag and randomly selects a sugar cookie? Okay, so summarizing that with a little notation. We got the probability that he eats a chocolate chip. I'm going to call that CC for chocolate chip. First. And he gets a sugar second. And the catch is that he eats that chocolate chip. Eats. And so I'm going to try and draw a tree to figure this one out. First thing I need to know is how many cookies are there all together? 8 and 4 is 12. 4 is 16, and 8 is 24?
Mm-hmm.
Okay, so we have 24 cookies. Question? Oh, you can't read them? Come sit right here. There are 24 cookies altogether. So I'm going to make a tree and I'm going to draw out probabilities as I do it. So he reaches into the bag and we know he gets a chocolate chip cookie. How many chocolate chip cookies are there? Well, there are 8 of them. So what's the probability he chooses a chocolate chip cookie? 8 out of 24, or 1/3. Yeah, I'm going to go 8 out of 24. Okay, now it's possible he didn't get a chocolate chip cookie, right? So I'm just going to put a little not chocolate chip down there. Let's see, if there's 8 cookies that are chocolate chip, how many are not chocolate chip? 16. So the probability he didn't get it one is a 16 out of 24. Okay, so then he reaches back into the bag and we're concerned about him getting a sugar cookie when he reaches back in. Now, would you agree he either gets a sugar cookie or he does not get a sugar cookie? Right? He's going to get a cookie. It's either sugar or it's not. How many sugar cookies are in the bag at this moment? There are 4. Divided by how many cookies are in the bag? Yeah, he ate one, so there's only 23 now. So the denominator changed from one trial to the next. That means these events are not independent. Okay, I lose independence. So when I'm rolling dice and flipping coins, we usually have independence. When I'm dealing cards and you get to keep them, I lose independence. It gets a little harder to work with. That's like why calculating poker hands, for example, are quite complicated. Because the cards don't go back in the deck. The denominator changes. And so let's see, there are 23 cookies. There's 4 that are positive, that are favorable for him. So that means there's what, 19 that are unfavorable? So there's 19 cookies out of 23 that are unfavorable. Now, all I really care about is this stream of events right there, that particular time stream. Now, I've adjusted the denominator so I actually can multiply now because I changed the denominator to 23. So the answer here, because we adjusted the denominator, is 8 out of 24 for the first try times 4 out of 23 for the second try. So, and we can multiply that out and clean it up. So let's do that quick and get an answer. The online homework claimed that the answer was, which one is this, number 6? About 6%. Let's see what this comes out to be. So whipping out our calculators, we've got 8 out of 24. Notice I'm not even worried about reducing stuff because I have these fractions and then I can multiply and or add and get some answer, and usually a decimal or a percent will do. Say what's next, times 4 out of 23. Enter, and I get 0.057-ish, so about 6% is what the online homework claimed it should come out to. And we get a tree that comes up with about the same answer, so that feels pretty good. Now, I want to talk about the idea of independence again. And that gets rolled up with another idea called conditional probabilities. So let's see. I had an example and I forgot to write it down. Let me see if I can remember it now. I think this will work. So consider the recent election. We had Trump running and we had Clinton running, and people voted. And for most people, pretty much we designate ourselves as men and women. Okay. And the exact statistics, I guess I could look it up. Let's see what they say. Trump voter demographics, maybe? We'll look at that. It come up when I searched. And let's check out, New York Times, election polls reveal a starkly divided nation. All right. And, they have graphs. Let's check out the graph. Okay. Oh, check it out. Clinton versus Trump and gender, male and female. Okay, so let's see. For male, it was 53 for Trump, 41 for Clinton, 53 to 41. 53 to 41. And we lose a few people in the middle who didn't vote for either, but that's okay. And then we have what? Let's see, 42 to 54 for women. And we've got this other category to throw in there. And so let's see, what's other going to be here? 6 in the other category there, and what, 4 in the other category here? Yep. Okay, so if I'm just talking about people, not percentages for a moment, how many people were surveyed to get this data?
100.
100? Almost. There were 100 men.
200.
How many women were there? Another 100. So Fen says there were 200 people altogether, the way I've collected my data here, if I'm counting those as just people, not percentages. Okay. So when I look at, for example, this number right here, 53, that would be the percent of people who voted for Trump, capital T, sorry, knowing that they are male. Right? 53 out of all the males, there's 100 of them, would be 53%. So whenever you have a probability that's contingent on being part of a group, that's called a conditional probability. And bottom line, I bet 99% of the percentages that you see in the news are conditional. They reference some group when they're giving the percentage, okay? Does that mean 53% of men voted? No, right? It's not of all the people who voted. It's of the people who voted, of the men who voted then for Trump, okay? So knowing some information changes your denominator in a sense, okay? Because in this table, really, I have 200 individuals. 53 out of those 200 were men who voted for Trump, okay? So the 53 represents being a man and voting for Trump. Notice I'm using the word "and" to connect them, okay? It's the intersection of this column with that row, okay? So conditional probability means change the denominator. What do you change the denominator to? You change the denominator to what you know, okay? And so with conditional probabilities, they're often written like this. What's the probability of voting for Trump And then they put a vertical bar to state what you know about those Trump voters. Ah, we know they were men. Okay, that's called a conditional probability. And the bottom line, what a condition does is it changes the denominator. Where are my colors? And when we have a table, conditional probabilities are easy. We just pick which row, that's the condition, or which column. And then we find which spot in that row or column we need that number of people or things. In terms of like definitions, like with probability notation, it's often written like this. The probability that some event A happened, knowing something else about it, B, like the probability somebody voted for Trump, knowing they had to be a male, is always going to be equal to the probability that somebody voted for Trump and they are male, divided by the probability of what you know, that they are male. So I'm just going to use that table to demonstrate this formula and show we still come up with the same answer. But there's other ways to use this formula. But that's the main one. So looking back at my formula here, let's see. Voting for Trump and being male, there are 53 individuals that fit that description. Out of a total of, there are 100 in that row and there are 100 in that row. So altogether, there are 200 things in my sample space here. So the probability, according to this table, of A and B happening, that would be 53 out of 200. The conditional rule says you have to divide that by the probability of just being male. All right, so according to this table, how many men are there? 100. And there's 200 people altogether. So that means in the denominator here, I'm going to have a 100 over 200. We're going to clean up that fraction. So new page. So right now, I'm going to write it slightly different. I have 53 over 200 divided by 100 over 200. Just to separate, what's the main division bar? That's the main division bar. How do you deal with division of fractions? Flip the second one. Yeah, you multiply by the reciprocals. So this must be the same as 53 over 200 times, instead of 100 over 200, I need to flip it. It's 200 over 100. And anybody remember the trick about what you can do before you multiply? You can cancel. Because this right here says I have 200 divided by 200. What's 200 divided by 200? 1. So that means this cleans up to be 53 over 100, which is what we saw looking at the table. So what's my point? Why the hell did I introduce this insane formula? Because it is useful in a lot of circumstances where you don't have a table. And even if you do have a table, it still can be useful. Right? And we're going to use it in another context in a problem in just a minute. Okay. So this is important. Again, conditional probability. And it takes some getting used to. So please watch the videos and read the book about conditional probability. You want to know the probability of something happening, knowing, that's what the vertical bar means, that something else happened. And that's always going to be equal to the probability of the first thing and the second thing happening together, divided by the probability always the second thing can happen, the thing you know about. And the easiest way to think about it is really all that happens is your denominator changes. Okay? You just focus on a slightly different denominator because you have a new, that knowledge gives you a new context. Twisting this formula just a little bit, I could take this probability of B in the denominator and throw it to the other side. If I do that, then the formula is going to look like this instead. The probability of A given B times the probability of B is equal to the probability of A and B. And usually that's written in the other direction. The probability of A and B is equal to the probability of A given B, that's a B, times the probability of B. Does that look familiar from a few screens ago? Maybe yes, maybe no. Madeline's looking at me like I'm nuts. Remember I talked about, I am nuts, but yes, but there is something. Remember when I talked about independence? If two events are independent, there we go, then the probability of A and B is equal to the probability of A times the probability of B. What's the difference in these two formulas? Don't they look a hell of a lot alike? Is there a difference between the blue in the middle and the black at the bottom? Don't see it? I see one difference right here. This has the conditional probability. This has just the probability of A. So what does independence mean? Well, independence means nothing else matters. No future event affects what's going to happen, like flipping a coin. So this would be like saying, what's the probability of getting a head on the first, knowing you get a tail, sorry, a head on the second, knowing you get a tail on the first? Does knowing you got that tail affect what's going to happen on the second flip? The answer is no. So that the key is, if events are independent, then any extra knowledge changes nothing. Changes nothing. So we can't take independence for granted. Sometimes it's very important. It turns up to come up with conditional probabilities. And if things are independent, that means any condition is irrelevant. Doesn't count. Doesn't do anything. All right, so we will come back to that in a minute. Let's see, what was another cute problem in the book? That wasn't too bad. All right, we'll do a not too hard one, then we're gonna do a really hard one. How about number 9? Actually, let's look up number 9 in the homework. Probability. Exercises 9. Okay, so we've got this data about students that got A, B's, and C's and whether they're male or female. And we want to find the probability that a student was female given they got a C. So we have a conditional probability here. So let me copy a bunch of things in my notebook and we'll try to solve this. So we need a screenshot. Come on. There we go. So we need this table. And then we need the question. Oh, too big. Get back here. Apparently that's as big as I can make it. Oh well. So in shorthand notation, I want to find the probability that a student was female knowing or given they got a C. So first we'll do it by the definition. And the definition says, first find the probability that they are female and they got a C. Okay, so an and is just an intersection of a row and a column, really. So let's see, here are my C's, right? And here are my females. So that means this probability is 15 females got a C out of a total of 65, right? Well, I'm doing the definition, so I'm trying to follow this rule right here. It says for a conditional probability, do the and first, and then do the probability of the condition. And then we'll do it the way you're mentioning there. So just to show we got a couple of tools in our belt. All right, so then I want to divide that by the probability of just getting a C, because that's my knowledge. All right, so let's see. The C's, there were 17 of them out of 65. And the cool thing about this formula here is think about fractions. You can multiply top and bottom by the same number, and that doesn't change the fraction, right? Like 1/2 to 2/4. Same thing with division. These 65s divide out, leaving what behind? Well, it looks like they leave 15 out of 17 behind. Okay. So now I'm just going to do the problem a slightly different way by looking at the table. So let me clean. Let's see, I need you to go away. And bless you. You go away and you go away. All right. So what's the condition? What do we know here about the students that we're trying to find the probability for? What's given? That they got a C. So that's all I care about. All I care about are the students that got a C. So now I don't care about the rest of the table. All I care about is that column. How many people are in that column? 17. Now, out of those 17, I need to know how many are female. 15. Boom, done. So I mentioned earlier, conditional probabilities are super easy if you have a table. Excuse me. You use the condition, what you're given or what you know, to narrow down what you're working with. And then from there, you find any other thing you're looking for, like in this case, the females. And that's it. So that is what I mean by a condition. Knowledge changes your denominator. So instead of having to worry about all 65 students, I only care about the 17 Cs, because that's what I know. I know they got a C. I was given the information that they got a C. Right? All right, now we're going to jump things up 4 notches. So bear with me, we'll do this twice, at least. We're going to take a look at question number 10. Question number 10 is rather complicated. And we're going to have to build a table like this to answer question number 10. There's a video that goes over building a table or building a tree. And I like the table better than the tree, so I'm not going to bother with the tree. All right, let's see, number 10. So 10 and 11 and 12 are similar. They're all quite challenging. And what's that? This is a very hard problem, yeah. So let's see, paste her in there, and then I should be able to, no, that's not what I wanted to do. Well, I guess I want to blow that up. There we go. See what doubling the size. Okay, so hopefully everyone can read that. So a certain virus infects 1 in every 400 people. Okay, so that's important. We need to know that 1 in 400 are affected. All right, a test used to detect the virus in a person is positive 90% of the time. Okay, interesting. So detect the virus positively 90% of the time if the person has the virus, and 5% of the time if the person does not have the virus. Okay, so they're giving us conditions on those numbers. Those are conditional probabilities. So that means those numbers are only part of a row, the 90%, or a column, depending on how we set up our table. They're also telling me here that the 5% is known what's called a false positive. Okay, so we gave somebody the test, it came back positive. Oh, I'm sorry, you've got the virus, but you really don't. Okay, so we falsely declared a positive. Right? Is that a good thing or bad thing? That's bad, yeah. Well, what's worse is a false negative, right? I'm sick, they test me for the virus, says, hey, you don't have the virus according to our test, but I really do and they don't treat me, right? That's bad. Depending on the treatment, maybe the treatment's not that bad. Okay, a false positive might not be as big a deal, but it just kind of depends on the situation. All right, so that's the information we have to deal with. So we're going to try and put that in a table. All right, so let's see. Can I squeeze the table in here? It's going to be a little tight, but we'll try. All right, so two kinds of information I have to deal with here, whether the test was positive or negative and whether somebody has the virus or not. So it's kind of like the coin situation. So we have test for positive, test ends up negative. So that's going to be some columns that generate here. And then whether the person has the virus or not. And then I'm going to have some totals to deal with also in this. So this is going to be a total column, total extra letter there, apologies. And this is going to be a total row down here. Okay, so what we start with is the first bit of information that 1 in 400 people has the virus, okay, in a general population. And there's lots of ways to deal with this. What I'm going to do is I'm going to deal with fractions of people. The video shows a slight variation on this. So either someone has the virus or not. Out of 400 people, what does this say? How many will have it? 1. That 1 is a total over there. Okay. How many people altogether are we talking about? 400. That is the total down here. So there's 400 people. If one of them has the virus, how many don't? 399. Okay, so we have one row of our table figured out. So that's where we start. Information about how infectious this virus is. All right, next thing, let's see if we can use, let's see, the test used to detect the virus in a person is 95% positive if the person has the virus. So they're talking about people that have the virus. That means I'm in this row right here. And they're telling me that 90% of these people right here have the virus and tested positive. Okay, so let's see, 90% of 1 is 0.9. So I'm going to put a 0.9 of a person here. If you don't like fractional people, then you have to multiply these by like 1,000 or 10,000. Okay, usually it's like 10 or 100,000 people you have to consider before you get no fractional people. We're just going to deal with fractional people. All right, if there's a 0.9 here and it has to add up to 1 in that row, what does the negative for the virus test have to be?
0.1.
That's got to be 0.1 right there. Okay, so we got that one figured out. Okay, so next we got to deal with that 5%. So let's read that again. 5% of the time, let's see, and 5% of the time, okay, so it tests positive 5% of the time when the person does not have the virus. So we are, let's see, read that again. Test used to detect the virus in a person is positive 90% of the time if the person has a virus, and 5% of the time if the person does not have the virus. Okay. 5% of the time when the person does not have the virus, we get a positive. All right. So let's see. Tested positive puts me in this column. Person doesn't have the virus puts me in that column. 5% of the people that don't have the virus test positive. How many people do not have the virus? Okay, what's 5% of 399? $19.95 people. 19.95 goes there. So let's just color code a couple of things here. Let's see, that 5% will make you color coded in blue. Oops, wrong blue. I want the highlighter. Blue. That's that number, which led us to that number right there. And then let's see, the 90% led us to this number right here. Okay, so we dealt with the positives. So filling in the rest of the table isn't too bad. From here, we've used all of the given information. If there's 399 people in this second row and we've accounted for 19.95 of them, find me the remaining number of people for that row. It should just be a subtraction. What is it again, sorry? 379.05, that looks right. Okay, and now all we have to do is add coming down to finish these columns. So let's see, that's going to be 379.15. And this one over here is going to be what, 5, 8, 20, wait, I lost track, 9, bring the 1, yeah, 20.85, right? All right, so now we filled out the whole table and we can answer the question. So again, the things I had to do is I had to use the 1 in 400 right away. Right there, right there. And then I could use the 90% and the 5% and then fill in the rest of the table. So we'll do another one of these in a minute with a different set of numbers. The question we were supposed to ask, well, let's see, they gave us A's and B's. Let A be the event that the person was infected. So that means, let's put in a red, A, person has the virus, and B, the person tests positive. Those would be the people in that column there. Okay, so where's my question? All right, we then need to find the probability that a person has the virus given they have tested positive. Okay, so remember, we have a table, right? The table means we can just focus on first what we're given. So what are we given? We are given that they tested positive. So for question A, I only need to worry about the positive column, the column that I labeled B here. Okay, so what's my denominator going to have to be if I'm focused on the positive column? 20.85, correct, yeah. And then in that column, I'm only concerned about the probability that a person has the virus. Okay, so new page, we want the probability that a person has the virus given that they tested positive. Looking at our table, 20.85 people tested positive altogether, and 0.9 people actually had the virus. And so now we just do that division and see what we get. 0.9 divided by 20.85, and we get about 4%, 4.3 if we went to the nearest tenth of a percent. .3%. So 4.3% of the people who tested positive actually had the virus. What do I want to do? I need my tools back. All right, next problem. Here, next we want to find the probability that a person does not have the virus given they tested negative. So the given information is a negative test. So that means we want to focus on this next column here. And they're calling that B prime, or that's they're not B in this column. So we have 379.15 people to deal with out of 400. Oops, where'd you go? There we go. And we want to know what is the probability in that group that the person does not have the virus. So the probability of the person does not have the virus given that they tested negative. And the tested negative group, what was that, 379.15? And the not viral is our 379.05. 379.05, and so we have to do that calculation. Calculator, Google, 379.05 divided by 379.15. I get 99.97. I have to go out to 4 decimal places before it's not 100%. 99.97. Okay, so of all the people who tested negative, 99.97 of them didn't have the virus. That's pretty good. Yeah, I'd say this test is doing all right, given that information. Let's see, what else? Is there anything else I wanted to mention about that? I think that's it. Let's try another one that's similar. Well, let's see if we did it right. They want a percentage and accurate to 1 decimal place, so the 4.3 should be adequate. And here, accurate to 1 decimal place. Ooh. Well, accurate to 1 decimal place would be 100%. I'm afraid to type that. Just doesn't seem right, does it? I'm going to type the 99.97, see what happens. Submit. Oh, it liked it. What if I tried resubmit? Can I resubmit? Oh, I can, yeah. What if I tried 100? Oh, I like that too. Cool. All right, let's try another one. 11. Okay, so this one is similar. So let us blow this up and stick it in our table. And so I want you guys to try this, given what we just went over, and see if you get a reasonable answer. Screenshots. This problem. All right, and the question, let's make it a little bit bigger. We are trying to answer, oh, it's in there. Compute the probability that a person who tests positive actually has the disease. Okay, we got everything we need right there. All right, see, based on the problem we just did, if you can make a table for this and come up with that answer, and then we'll compare notes. So see if you can mimic that last table. I'll write it down too, and we'll go over it together. So I will draw the initial table. Let's see, I need a pen to do that. Work. So we have positive, negative, disease, no disease. And then we have totals. Did the fractional people freak anybody out? Okay. So if the fractional people freak you out, then what the videos recommend, and the book does too, is to take this number, like the 1 in the 400, and multiply it by 1,000 or 10,000. And then you'll eliminate fractions here. So here, 1,000 would do it, 100 would do it too, because I only have 2 decimal places to get rid of. So in this one here, if you wanted to get rid of fractional people, then you could do, I guess I would probably do 10,000 people. So I'm just going to put that as a possible starting point. And you will likely have no fractions. What is the incidence rate? Anybody know what that means? Yeah, how many people have the disease? Yeah. So in this case, we want 0.5% of 10,000. And that's what would go in this box right here. All right, so you guys go from there. It's a little starting point. Let's see, whip out my phone calculator. Is anyone clear on what a false negative is? Is anybody not? No questions? Okay. All right. So try something, come up with an answer, see what we get. Oh, 10,000 wasn't enough people. Oh well, I tried.
Mr. Parker, how did
Yep.
you come out with the 10,000 people total?
What's that?
How did you come up with the 10,000 total people?
I had to make up some total population to work with, so I just picked 10,000.
I see. Okay.
Yeah, you could pick 100, or you could pick 1,000, or 100,000, or 1,000,000. Any number will work there.
All right.
Okay, so unless I messed up, I'm getting the answer is about 9%. So I'll have you guys help me in just a minute. I'll give you a little more time to figure. All right, ready or not, let's give it a shot. So in any of these problems about diseases and viruses, you always start in the totals column on the right, talking about the disease or not having the disease. And usually we're given like 1 out of so many, or we're given it as a percentage, how the disease occurs in the population. So here, given a 0.5%, I decided to start with 10,000 people. Why 10,000? Why not? I just picked that number. Next thing we need to do is start using the other information I'm given. And so, for example, a false negative is 5%. Okay, so that means I'm talking about negatives, right? But it got a negative result when it shouldn't. That would mean I'm talking about people in this box. Okay, so 5% of the people who had the disease tested negative. It said they don't have the disease. That's a problem. So that 5% is of this 50. So what's 5% of 50? Oops. 2.5? Is that right? Somebody help me out? Yep. Okay.
Yeah.
So I get that right away as my second step. Okay. So now I can finish that row. If 2.5 of those 50 people tested negative, that means it should have been what? 47.5? People had the disease, tested positive. So I've used up my false negative information. So now I move on to the false positive information. Okay. So they tested positive. but it's false. So that is going to put me in this column right here, in this cell right there, right? They tested positive, but they really don't have the disease, okay? So 5% of these people that don't have the disease. Now at the moment, I don't have those people, but can I find them? Right, I just need to take that 50 out of the 10,000, and I think, that's not a pen, 9,950. Excellent. And let's pick a new color for that. No, we'll just go with black. 9,950. Okay, so now I need 5% of the 9,950. I got 497.5. Anyone else? Or did they do that wrong? 0.5? Yep, okay. So that's what I'm gonna put here. And let's label that blue. 497.5. And we can totally fill out the rest of the chart with some subtractions and additions. Before I do that, I'm just gonna get down to see how much more I actually need to do to answer the question. I want to find the probability that a person who tests positive actually has the disease. So breaking that down, I'm trying to find the probability that somebody has the disease, given that they tested positive. And that's the hard thing about this. The language is always hard to maneuver. What the heck's a false positive mean? Okay. And the last question, compute the probability that a person who tests positive, so a person who tests positive, that's a statement, okay, actually has the disease is the question in this case. So I need to look only at people who tested positive. So at this point in time, reading that question, I only need this column right there. Let's make that in red. Which means I need that total at the bottom. So let's see, what do I get when I do that? That adds up to a 1, 14, 15, 14, 5, 45 when we add those together?
Yes.
Okay, so of the people who tested positive, there we go, what's the probability that they have the disease? So that means I want this number divided by that number right there. So let's whip that out. If I type that right, that's where I got about 9%. 8.7 to the nearest 1/10 of a percent. All right. Okay, so now let's make sure we didn't make a mistake. Well, there's two ways we can do that. We can fill out the rest of the table, make sure everything lines up, right? So that when I do my subtraction to get that number and addition to get that number, I would want to confirm that the numbers across the bottom here add up to 10,000. So that would be one way to double check. Other ways to double check, reassure yourself that you identified the position in the chart that leads to a false negative and the position in the chart that leads to the false positive. Again, that's a little bit tricky too. And a beautiful thing about the homework is we got to check your answer and try another problem button. So this is one where you're going to want to try it a couple of times. So let's see, what do we think the answer is? Oh, they said accurate to 3 decimal places, but they don't say enter it as a percent. So that means I believe they want me to type 0.087. And the video here, I think you should find quite helpful. It's very much like what I did here. And I'm going to hit submit. There's an error. Oh, I hate when that happens. Let's try one more time. Are those the same numbers? Yeah. 0.87. Oops, wrong 0. Submit. All right, the page broke, so I can't test it. Well, yeah, I broke it. It's right. Yeah, I'm sure it's right. All right, so unfortunately we have no class on Friday. Because of that, I'll extend the homework through Monday night for anybody that needs it, so you can ask me questions on Monday in class. So I'll leave some time Monday in class for you to ask questions. But please try everything before then, and then we can go over stuff some more on Monday.